So we're going to be looking to find the absolute extrema of a function on a closed interval. This question specifically asks us to find the absolute extrema of the function f at x equals x to the 2/3 times quantity 6 minus x to the 1/3 on the closed interval minus 1 to 7 inclusive. So the first thing we're going to do is take the derivative of this function. And we can see here that we're looking at a product rule. We could imagine splitting this function right there. And we have a u and we have a v. And so we're looking for f prime at x is going to be u prime, which in this case is 2/3 x to the minus 1/3 times v, which is 6 minus x to the 1/3, plus u, which is x to the 2/3, times v, which is going to be 1/3, which I will pull out into the front here, 6 minus x to the minus 2/3. And then I have to remember my chain rule here. I imagine I have a box around that, and so the derivative of what's in that box is going to be a minus 1. So I have a times negative 1 coming out, which I'm going to just move to the front of the expression. And I'm left with that as my derivative. I'm looking for the critical values of this function, which means I need to decide where does this derivative equal 0 and where does it fail to exist. So we start by looking at where it equals 0. I don't really like the way that this function is set up. And so I would probably begin actually by rewriting this in a nicer form. So I would take this piece and move it to the denominator, and I'm going to be left with here in the denominator a 3 times the cube root of x. And in the numerator I've still got this 2, and now I've got the cube root of 6 minus x. That's a little bit easier to see. I'm going to do the same thing with the other side. Here I'm going to have in the numerator a cube root of x squared, and in the denominator a 3 times the cube root of 6 minus x all squared. That's going to be a little bit easier when I try to solve it, I think. So now I'm going to look for my critical values. I begin with f prime equals 0. And I see that if I set this expression up here equal to 0, the second part of the expression is going to become positive when I move it to the other side of the equation. So I'm going to be left with 2 times the cube root of 6 minus x over 3 times the cube root of x squared, of x, equaling the cube root of x squared divided by 3 times the cube root of 6 minus x squared. I can now simplify this by multiplying both sides of the equation by that denominator, which will cancel it out of there and end up multiplying it into the numerator there. And I can multiply this 3 times the cube root of x across, and it'll get rid of it in the denominator here, and multiply the numerator on the right side. And so I end up clearing fractions that way. So here I'm going to be left with 2 times 3, which is 6. And the cube root of 6 minus x times the cube root of 6 minus x all squared gives me the cube root of 6 minus x cubed. And those things cancel, the cube and the cube root. And so I'm just left very nicely with a 6 minus x. The same thing happens on the other side. I get 3 times the cube root of x times the cube root of x squared, which is the cube root of x cubed, which is just x. So I can now finish this off very easily. 36 minus 6x equals 3x. So 36 equals 9x. And we're left with x equaling 4. So I have a critical value at x equals 4. Now I have to look for the places where f prime fails to exist. And if I look at this expression up here, I can see there's only 2 places where this is ever going to fail to exist. I don't have any even roots, and so I don't have to worry about that. I don't have any logarithms or any inverse trig functions, so I don't have to worry about those. The only thing left to concern myself with is division by 0, and that's going to happen when x equals 0 and when x equals 6. So I see that I have 3 critical values that I need to worry about. Now, in order to decide what the absolute extrema are, I'm going to use a process called the candidate test. The candidate test says basically, if this function has absolute extrema, they're going to occur in one of two places, at a critical value, of which I have 3, 0, 4, and 6, or at an endpoint, either -1 or 7. And so really, those are the only 5 places where I could possibly have an absolute extrema. And so all I need to do is evaluate the function at those places. So I want f at -1, f at 0, f at 4, f at 6, and f at 7. Those are the only possible locations where an absolute extrema could occur. And so if I look at those 5 and choose the largest, it therefore must be the absolute maximum. And if I look at those 5 and choose the smallest, it therefore must be the absolute minimum. So f at -1, I substitute a -1 into my original expression, and I'm left with -1 to the 2/3 times 6 minus -1 to the 1/3. -1 to the negative 2/3. Sorry, that should be -1 to the positive 2/3. -1 to the 2/3 is -1 squared, which is 1, and the cube root of that is 1, so that just becomes 1. 6 minus -1, of course, is 7. 7 to the 1/3 is the cube root of 7. F at 0 is 0 to the 2/3, and it doesn't really matter after that. That's going to be 0. F at 4 is 4 to the 2/3 times 6 minus 4 to the 1/3. 4 to the 2/3 is 4 squared, is 16, the cube root of that. So I want the cube root of 16. And here, 6 minus 4 is 2, and so I want the cube root of 8. Sorry, the cube root of 2. And the cube root of 16 times the cube root of 2 is the cube root of 32. I could simplify that a little farther, I guess. I could take an 8 out of there, and I'd be left with 2 times the cube root of 4. But I don't really see where that's going to help me. I'm just trying to compare which of these is the largest, and so I think the cube root of 32 is maybe just as good. F at 6, well, when I put a 6 in here, I'm going to get 6 to the 2/3 times 0, and again, that's 0. And F at 7 is going to give me 7 to the 2/3 times 6 minus 7 to the 1/3. 7 to the 2/3 is the cube root of 49. And 6 minus 7 to the 1/3 is the cube root of -1, which is -1. So these are my candidates. These are all the possibilities for absolute max and absolute min. I can see that the first 4 of these are all positive, and the last one is negative. And so therefore, it's clear that f at 7 is my absolute minimum. So I'll just label that over here so that I don't forget. That's my absolute minimum right there. Now I'm left with choosing the largest of the remaining 4 possibilities for the absolute maximum. Well, I can see that 0 and 6, at 0 and 6 I'm at 0 in both places, and f at -1 and f at 4 are both greater than 0, so I can rule out 0 and 6. And now I'm just left with deciding which is larger, f at -1 and f at 4, and clearly the cube root of 32 is bigger than the cube root of 7, and so this is my absolute maximum. This process of finding absolute extrema in this manner is called the candidate test. And what we're basically doing is we're looking at all of the critical values and looking at the endpoints and deciding which is the largest and which is the smallest. I don't have to justify anything because I already have. I've justified by saying these are the only 5 places where an absolute extrema could occur, and I've looked at all 5 of them and chosen the largest for the absolute maximum and the smallest for the absolute minimum. So it's already justified. This is a good way of finding absolute extrema. If the question, however, asked me for local extrema, I wouldn't be done. I'd still have more work to do because f at -1, f at 0, and f at 6 might be local maxes, might be local minimums, might be neither, and I would have to do a labeled sign chart and do a bunch more work to figure that out. But since I'm only asked for the absolute extrema, I've done everything I need to do now. I can just write up a final statement, and I can say, therefore, f has an absolute max of the cube root of 32 when x equals 4, and an absolute min of negative cube root of 49 when x equals 7. I'll leave it to you if you want to check that in the calculator and graph the function to confirm that that's right, but this is a good way of finding absolute extrema on a closed interval. Remember, the extreme value theorem tells me if I have a continuous function, which I do in this case, on a closed interval, I have to have both an absolute minimum and an absolute maximum, and now I found those.